Should we start, Bharat?
Yes, please.
Yeah. So it is really my pleasure to introduce today's speaker for the webinar, Professor Alessandro Pastore. He did his PhD from University of Milano in the year 2008, and then he did his first postdoc from the University of Jyväskylä, Finland, and then he moved to France. He did his next postdoc from IPNL France, and then he did the third postdoc during 2013 to 15 from ULB Belgium, and then 2015 he joined as a faculty at University of York, England, and he has been working on developing a new nuclear energy density functional, and this is something which is very much challenging, and I mean, with a lot of experimental data pouring on the finite nuclei, exotic nuclei, and neutron stars, and very accurate data has made, I mean, the life of theoretician very challenging. So basically, I mean, we are looking for a kind of a unified nuclear energy density functional which can describe not only the finite nuclei along the stable and the exotic along the drip line, but also can explain the neutron stars, which are very dense compact object. And today he will update us the latest status of this kind of density functional. And I'm sure that, I mean, he will tell us his contributions too, because he has been very actively involved along this direction. So today he will talk to us about the nuclei and the stars with the new kind of functionals. So Alexandro, please.
Okay, thank you for the very nice introduction, and thank you all for the time devoted to this webinar. So it's my pleasure to discuss and present some of the work that I've done on this topic. And I have to say that the title is more ambitious than what I will actually present, because although it's true, I would like to have this unified vision of nuclei and stars, the reality is quite different, because before getting there, it requires a lot of steps. So I will try to discuss the different projects that I'm working on the different parts of the stars. I will discuss this a little bit later, and eventually in long term doing this in a proper and unified way. At the moment, unfortunately, one would like to use a unified description, but this is not the case, and actually most of the time is not the case. So the topic of interest are neutron stars. So I don't want to discuss too much. This is a very famous object now due to the recent measurement of gravitational waves. So this is on the press. From my point of view, neutron stars are big nuclei, right? So these are very dense objects with relatively small radius, small compared to other stars, right? The radius is roughly 10 kilometers. We don't debate here on the exact value. And with a mass of typically 2 times the mass of the sun. So if you work out in a simple model, the density, turns out that the density should be 3-4 times the typical density that you find in an atomic nucleus. Now, this is, as I said, from my point of view, I'm a nuclear structure researcher. So from my point of view, this is a nucleus. This is a nucleus with some, of course, warnings, because what matters is that, from my perspective, in a neutron stars, we have fermions, we have neutrons, that they interact via strong force. We can discuss eventually other particles later on. So from the point of view of the interaction is the same that I find in a nucleus, of course, in a different density. So I have to, in principle, I could use the same model. I will explain which model, the density functional, but it is an extrapolation, because none of the models that we have on the market, apart from QCD, are fundamental models. They are always rely on adjustment of coupling constant. So whenever you adjust coupling constant on finite nuclei and you extrapolate and you test your model at the density that are 3 times, 4 times, 5 times the densities of finite nuclei, you are extrapolating. So there are big warnings in terms of this extrapolation. So the structure of the star is more complex than a big nucleus, as I said at the beginning, because we have such big mass. So we have strong gravity, strong pressure. So matter organized within the stars under different forms. So if we go from the outside to the inside, so if you take this left left panel figure that is very famous, you will see that the neutron stars has an onion-like structure, right? So we have different layers going from the outside to the inside, so low density to high density. These layers have an increasing density and they have different structures. In the most external layers, we still find nuclei, okay, that organize themselves in a lattice, but these nuclei are standard. They become more and more neutron rich while we increase the density, so we go toward the inside of the star. But then we find immediately more exotic phases. So when nuclei start to get more and more neutron rich, as you know, we encounter the neutron drip line, right? Atomic nuclei do not exist for an arbitrary value of neutrons and fixed number of protons. So what happens is that these neutrons start to drip off, and we enter in a first exotic phase that is called the inner crust, where you have a very nice coexistence of nuclei and the neutron gas. So here you see already we move away from what we know on Earth, because it's not a condition that you can recreate on Earth. So we already need to use models that have been created to reproduce observable, measured in a laboratory, to discuss a system that is quite exotic and quite different from a nucleus, right? We don't have a nucleus surrounded by a gas of neutrons. This is not the end of the story. Of course, we can go deeper and deeper into the star. So these gas of neutrons becomes more and more important. So the neutrons contribution becomes more and more important. And eventually, we don't have any more structures. So we enter in a liquid phase. So we have protons, neutrons, electrons, and other particles that coexist in a liquid phase. This is the so-called core region, and it's the inside region of the star that is marked with a question mark. Why a question mark? Well, because we don't know what's inside, right? At the moment, we have no clue. All the predictions on the composition of this core are based on models, and the models predict very, very different composition. There are plenty of issues on this topic, and I will gently touch on this at the end of the talk. But as you see, in a neutron star, we find something that is close to experiment or close to what we can measure only at the very surface. So the so-called outer crust region, which is the low density region. But immediately when we move further inside the star, we immediately find regions that are very different and very exotic. So, as I said, we use models that are tuned on properties of nuclei that are measured on Earth to extrapolate properties of these exotic phases. So here there is a huge warning that we should say from the beginning, that all extrapolations should not be taken as God-given, right? So if you fit a line through 2 points, the fitting is perfect, but then the extrapolation, how reliable it is. So whenever you move outside the region that you use to constrain your coupling constant, it's always an extrapolation, and as such, you have to treat it in a conscious way. And this is why for example, if you take the simplest calculation you can do in a neutron star is to calculate the chemical composition of the outer crust. So you want to know which nucleus appear as a function of the depth of the crust. So this is a figure again that is very famous and describes a tiny layer of the crust. And as I said, in this region you find the atomic nuclei. So in principle, our models are fitted to reproduce these properties, right? So one should be quite confident in this calculation. And what you see is that when you move from low density to high density, so from the outside to the inside, so on the outside we have nuclei that are measured experimentally, like iron 56, nickel, and so on. So when we do the calculation, we take the experimental values. Up to, let's say, 200 meters depth, when more or less we don't have any more experimental values because the models favors neutron-rich nuclei. So as you know, the neutron drip line is much further away than the current experimental measurements, so we have to rely on models. And here I compare two models that are two mass models, so models that are being created to reproduce nuclear masses. And immediately after the last experimental point, the next predicted nucleus in the crust is different, with two models that are fitted in the same way. So how reliable is this physics? So you cannot just take one model, run it, get some composition, some nuclei out. You will see that if you compare different models, you will get different results. Of course, they are not completely orthogonal results because what we observe is that although the nuclei are different, the common pattern is that nuclei tend to be semi-magic. So this is kind of robust result found also with other models. So you see this N50 and 82. It means that more or less in this region of the star, we are more keen to find semi-magic nuclei, neutron semi-magic. Then of course this is not a sufficient information, because if you want to use this model for calculating some astrophysical observable like gamma ray burst, then you want to know which nucleus is. It's not sufficient to know that it's a semi-magic, right? You want to know if it's copper or nickel. So my work now in these recent years has been on this aspect. So how do we build models, and how we do extrapolate, and how reliable are our extrapolations. So the model, as I said from the beginning, in a neutron star, we have nucleons, we have fermions that interact via strong force. So the most convenient model to use in this case, due to the different structure of the star, right? We have atomic nuclei surrounded by gas, eventually pasta phase. I didn't mention, but maybe some of you are working on that or aware of that are even more exotic structure. And then we have a liquid phase. So it's very hard to find a model that is able to describe all these different regions. At present, the one that is able to do this job is density functional theory. So we rely on Bergholm theorem. So the fact that a system of fermions with a given interaction can be described exactly by a unique functional. So we expect that if we find such a functional, then it doesn't matter if we describe a nucleus on Earth or a nucleus in a neutron star, the function will be the same and our description will be exact. Of course, this is not true because we don't have such an exact functional. It doesn't exist, or at least nobody found it. So we have to rely on approximation. So here we enter already in a discussion on how an approximated functional behaves. But let's assume that this is correct for the moment. So we want to find a functional, and the Horn-Bergson theorem is very powerful, but gives absolutely no indication on how to find such a functional. So there are different schools or different strategies on the market to find such a functional. For example, you want to ask yourself, do you want to consider or not general relativity in building a functional? So you want to use a relativistic, so-called relativistic mean field or non-relativistic mean field. So these are hypotheses that nobody is able to discard a priori. So these are choices that you have to make according to the system that you want to describe. So maybe, for example, if you want to work in an atomic nucleus, a non-relativistic description sounds reasonable. But if you want to describe the core of a neutron star, a relativistic description would be maybe more important. But this is not. This is just, let's say, speculation. Of course, you would like to use to rely on on the least number of approximation possible, but we know that that we have to face reality, right? So if when people speak about general relativity into functions, so they want to do relativistic mean field, in most of the cases they are not able to treat Pauli principle. So the question is, do you prefer to sacrifice Einstein or Pauli? So it's matter of scientific discussion, and this is not a solved problem. In my research activity, I always work on one type of functional that are the non-relativistic one for historical reason. And here in this slide, I show you one functional. It's not the only one, but it's the most popular. This is the functional that is derived from zero range effective Scherm interaction up to second order ingredient. So what is a functional? It's simply a linear combination of coupling constant, so this C, and the local densities. So once the functional form is fixed, so someone wakes up in the morning and say, this is my functional. So the only difference between functional now is in the coupling constant. So probably if you work in this domain, you are aware that we have on the market, I think 400 Scherm functionals that have more or less all the same shape. So what's the difference? Why they have different names? Well, the different names rely on the fact that they have different coupling constant, and this coupling constant have been derived using some fitting strategy. So as I said at the beginning, we are not doing QCD or QED. So we don't derive anything from first principle. We are doing an effective theory. So we approximate the interaction between nucleons with an effective interaction. So as such, we have to absorb our ignorance into the coupling constant. So we adjust the coupling constant to reproduce some observables. We then use the functional to make predictions. Of course, the process of adjustment of coupling constant is completely arbitrary. There is no unified recipe on how to adjust this coupling constant. And this gives rise to these, as I reported here, 240 Scherm models. Last update to 2012. I think that in the last 5 years, they published at least 40, 50 more models. Why? Because everyone has different ideas. The only common structure is, of course, the functional form. So these terms, in some cases, some of the coupling constant could be 0, okay? But the form is the same. What changes is the recipe that you use to fit this coupling constant. So maybe you have done also, some of you have done this in different contexts of fitting, but this is fitting, okay? So you have fitted a line, you fit a function in the same way. We have to decide a pool of observables, and then you build a chi-square, and you minimize your chi-square. And you have to make sure that the pool of observable is suitable to constrain all the different terms of the functional. Because, of course, not all nuclear observables are important to constrain the different terms of the functional. Example, if you look at this functional form, there is a so famous tensor term here. So tensor was a very famous piece of interaction that has been popularized by Otsuka at the beginning of 2000, and a lot of people try to fit tensor, right? But if you fit tensor on nuclear masses, as most of the people do, you will see no tensor effect. Why? Because the tensor is competing with other terms in the functional, so you don't see anything. So nuclear masses are not the best observable to fit a tensor. Maybe to fit a tensor, you would like to look at splitting of single particle states or some isotopic trend of splitting. But even that, it's not a clean observable. Well, first of all, it's not an observable, but it's not a clean way of fitting the tensor, because you have also spin orbit terms that come into play. So you would like to find maybe some excited states. So in some specific, maybe excited states in the nucleus that could be more clean observable to constrain the tensor. So this is, you see, it becomes very complicated business, because in the best scenario, you would like to find the right observable for each piece of your function in such a way that you give the best constraint possible. Otherwise, you would produce a functional with a poorly constrained parameter, and a poorly constrained parameters will give unpredictable results. Now, let's imagine that we have solved all these issues, although it's not the case, but we have fitted our functional, and we have finally our coupling constant. Well, the next thing to do is propagating errors. So what has been done here, I cite a couple of papers by the UNIDEF collaboration. So this work has been done mainly by Professor Nazarevich and Professor Reinhardt, the one who really started this work on statistics. So since you make a fit, right? So let's leave aside for 1 second a systematic error, of course, because this is built in your model. But whenever you make a fit, you have errors. And the error comes from your statistical error, right? So when you minimize a chi-square, the curvature of the chi-square surface around your minimum is your Hessian matrix. And this is telling you how, is giving you essentially the covariance. So it's giving you, the covariance is the inverse. So it's giving you the error on each parameter of your function. So when you want to use your function outside the region where you have made the fit, you should propagate the errors. So this is the error propagation for a functional, a Skirm functional. It's not really important which functional. So here there is green triangles are the residue, right? So they have fitted the functional against the masses. In this case, these are masses. And they plot the difference between the model and the experiment. Fair enough. And then the light triangle, light green, are the errors. So the propagated errors. And what you see is that your errors in the region where the residue exists, so it means in the region where you have done the fit, produce an error that is, let's say, reasonable, although probably is underestimated. But whenever you move outside the region of the fit, so here we are looking at this lead isotopic chain. So whenever we move outside the region of the fit, you see that the error grows a lot. And this is just the statistical error. So this should be taken into account whenever you make a prediction. And even worse, so what they've done, and this I find it very funny, here the authors have calculated the equation of state of dense matter with one of these functional, this SV mean, and they have propagated the error on this equation of state, and they use this propagated error on the equation of state to solve the Tolman-Oppenheimer-Volkoff equation, and so calculated the mass-radius relation, right? This is a well-known quantity. So if you look, the solid line is the predicted value for mass-radius relation, which is clearly below the observed data. But if you take into account the propagated error, only statistical error, you get the shaded area. So you see that you have a huge uncertainty. And this is just from statistics. How to improve these statistics? Well, you imagine you are fitting a nucleus, right? Maybe lead, and then you are extrapolating to a system that is composed by 10 to the 55 nucleons. It's a huge extrapolation. So the only way to improve the statistical error is to include information. And here, for example, they added 2 extra points. One is directly the mass, the maximum mass that has been measured for a neutron star and the radius. Okay, let's assume that these values are correct. We don't end the discussion. If you put this directly into the fit of your function, then you get these shaded dot lines that represent the area of uncertainty of a new function that has been called T of V mean, because it has been fitted using the previous one plus this new constraint. So in this case, the extrapolation, it becomes more reasonable. Of course, this is a matter of choice, right? But this is a little bit that is somehow the direction we would like to undertake. We would like to build functionals that can be used both in nuclei and stars. And if we want to use them in stars, you need to add as many information as possible on the physics of these stars. Otherwise, you are simply doing a huge and massive extrapolation that could be misleading. Of course, as you are aware, we don't have so many information, but we hope that thanks to the new measurement on gravitational waves, we will be able to get new insight on this object. So I try to speed up a little bit. You can see that I spent a lot of time on discussing this model. I wanted now to discuss what I've really done in terms of the different parts of the stars. And again, I show this picture to illustrate the different regions of the star. So we have the outer crust, where we have these atomic nuclei, eventually neutron-rich nuclei, surrounded by a gas of electrons. Then we have this inner crust, where we have nuclei surrounded by the neutron gas, and eventually we go to the core. So I will present 3 different works that I've done on the 3 different regions. So let me start with the outer crust. So this is again a picture on that discuss or present the chemical composition of the outer crust. In this case, created with 5 different mass models. So the way you determine the outer crust of a neutron star is always the same. So you always assume a single nucleus composition per each layer of the star, and you determine the chemical composition by minimizing the chemical potential. So you find the nucleus that has, or the nucleus that combined with the kinetic energy of the electrons gives the lowest energy contribution, right? The total energy. So you minimize always the energy, the free energy. So you get the different nuclei, each nucleus for each layer. And as I said, in the region where you have experimental measurement, all models agree, because of course it's the same model using always the same experimental masses. But whenever you move to extrapolation, it means that here you really need, as an input for your astrophysical calculation, to know the mass of nuclei. And you see that the results are very different. There are trends. So it's telling us that nuclei tend to be around magic, or at least semi-magic in neutron number. So we tend to stay around these shell closure, but the exact value is not really possible to have. And again, maybe it's not really relevant when you calculate the equation of state of a massive object and you are interested in maximum mass and radii, even the outer crust is not dramatically giving an impact, maybe a few percent. So it's really not really important. But maybe in other astrophysical observable like giant flares and so on. So here you need to know more in detail the composition. So my scientific question is how to do better, right? So one answer would be, yeah, you can refit the functional and repeat the job, but this is not really improving anything, because we have seen that in this previous picture, all these models, well, not all of them, but most of them have a very good reproduction of known masses. So the model like BSK8 or FRDM, these are mass models. So these are models that are fitted to reproduce masses, and they give the best reproduction on the market. They give an RMS, so a root mean square deviation of alpha MeV. So if you take a standard functional that has been fitted on more general properties, usually the RMS is worse, 2-3 MeV. So it's hard to do better, right? In the mass model game, it's hard to break the barrier of alpha MeV RMS over 2,000 nuclei, of course. So I decided to work a little bit on the statistical aspects. So I've done here some tests, and I used a simplified model that is called the Duflo-Zucker. Of course, I could do the same game. I could play the same game.
Alessandro?
Yes?
I have a very naive question actually. See, when we talk about the BSK models,
Yes.
see, they are basically obtained by fitting, some few thousand masses for the nuclei.
Yes.
Okay, now my question is the following: that we know that you see if you fit only the masses, so basically what we are doing, we are adding only one kind of data. Okay, and
Yes.
the rest all other kind of data. See, if I want to really have a proper fit of the model, I should use a variety of the data. Now, if you fit the model only based on nuclear masses, and you ignore rest everything like charge radii, I mean giant monopole, dipole, quadrupole, all those things if you ignore, and this model if is used, I don't know matlab, how much to trust. Matlab, this is my very genuine question. I always ask myself that how can I take a model just to fit one kind of data, and I mean this is my just very sincere query. I mean if you can answer this question.
Yeah, sure. So in this case, the BSK are not fitted only on masses. They are mainly used for masses, but in their fitting protocol, they also include radii, they include compressibility. But when I say that this is a mass model, is that BSK, the family of the BSK, is not strictly speaking a functional. It's a micro-macro model, because if you take a model like SLY4, this is a functional. So the functional is this form. While, but if you do that, SLY4 that is not able to get very close to masses. So you have a difference of 4-5 MeV. What the people in Brussels managed to achieve such an accuracy using a functional, let's say, they had to add extra terms. So they had to add some macroscopic term like microscopic term that are related to
basically that T1, T2, and T3 kind of term.
But yes, this makes the model a little bit dirty, because you have these correlation that are adjusted only to reproduce masses, and when you use the model for star, you switch them off.
Yes.
Because you don't know what is a particle vibration coupling in inner crust where you have a gas. I mean, all these things are switched off. So it's a very delicate model. I mean, you could raise a lot of questions on how to use this model properly.
Okay.
While if you take FRDM, this is only a mass model. So this is a series of parameters, and you want to just adjust masses. And then, of course, you cannot use it for other properties. So these models, you can use them only on the outer crust. So if your goal is, of course, to have a unified vision of the star, then you should stick to a functional.
Yes.
And
okay.
you're absolutely right.
Yeah,
But here, what I wanted to do is to play a game only on the outer cast. So as you will see, I will not be able to give a unified picture of the star.
Mm-hmm.
Okay, that would be in the long-term run. Now I wanted just to test the different parts. So here, what I presented, for example, it's a mass model. It's a Duflo-Zucker mass model. It's fitted only on masses. It's a kind of extended version of the liquid drop formula. So we only fit masses. So this does only this. And even if you do only a fit on masses, you realize that you are not good, because nuclear masses are complicated. And even if you focus on only one observable, like here, you see that your model is not able to fit correctly. Although if the RMS is very low, right, alpha and MEV, you are far away from the experimental accuracy, several order of magnitude. And if you look at the residue, so the difference between the model and the experiment, you see that if you have done a proper fit, you should see white noise. And you don't have white noise here. You clearly see arches. So it means that there is a systematic error.
Systematic error.
And this is quite common in all mass models. So we have to deal with systematic errors. And I will show how eventually to find a trick to remove this systematic error. So here is the summary. When you adjust the model, what you're doing, you're relying on this equation, right? You have some experimental observable, and you say that your experimental observable will be your model plus some white noise. So this white noise should be Gaussian, right, with zero mean and some variance. And then you can use, once you have fitted your model, you can use it to extrapolate. So what I wanted to explore here is, first of all, the error bars. So I wanted to propagate statistical errors, because when I compare, you see different models in this figure, I just compare the central value, but I didn't say anything about error bars. Maybe these models are all compatible within each other, given error bars. I don't know. So nobody did that. So I tried to have a look at this effect. So maybe this part I skipped. So I used some advanced statistical methods to improve the quality of the error bars. And here I compare, for example, the error bars that I obtain. So these are two isotopic chain. So this is nickel and copper. The red line is experiment with this error bar. So the orange line is the last experimentally measured mass. So when you see the error bars in the experiment are mainly extrapolation. So these extrapolation are based on local mass models. And the black one is the Duflo-Zucker. So these are the prediction of the model. And as you see, as I said before, in the region where masses exist, the model, let's say, does quite well. And whenever you move outside the fitted region, you diverge. You get very, very different results. Okay. So why? Well, because this is extrapolation. Here I try to reproduce, to improve the error bars, to propagate error bars in the models. But what it turns out to be is that the statistical errors are not relevant. Even adding statistical errors, I'm not able to get a compatibility with experiment, or let's say local extrapolation. Let's say that these local extrapolation are not really robust, but they are better than a model, because usually they are taken maybe from Q values of beta decays. So it's not strictly speaking a model, but you see, if the mass has not been measured directly, maybe we know something about a reaction, and we can infer from Q values. So these values may change, and actually they do change when the measurement is done, but let's say that are a good guidance. So what we have decided to do is, okay, let's see what's on the market in terms of statistics. So my model is not good because the residues are not good. It's not white noise. So something is left out. So two possibilities. Either I go back and I try to improve my model. So I try to add new terms, right? Here I use the Duflo-Zucker it's a 10 parameters model. Maybe I could add 11 parameter, 12 parameter, 13 parameter. Actually, this is not the right way. I can tell you immediately that if you play the same game with Duflo-Zucker 33, that it means that it has 33 parameters, you get exactly the same results. So that's not the way. So something is left and we don't know how to model it. So I decided recently, actually, because this is a work that I've done with a master student last year, we decided to look on the market, what's available. And we found that it's, in terms of statistical methods, there has been a lot of effort done in neural networks. So neural networks are, basically speaking, a fit. So you model, you create a model that is made by neurons, and these neurons are connected one to each other by weights, and these weights are undetermined. So you determine these weights by adjusting them on the data. The data here are the residue. So my idea is I can model the physics with a real model, and then what's left and that I don't know how to deal with.
So you
Yes.
With the residue, you try to do the neural network.
Yes.
Yeah. Okay.
Why I do that? In principle, you could apply the neural network directly on masses. The point is that neural networks don't contain any physics. They learn something, but you don't know what they learn.
Exactly.
So it would be very dangerous to run blindly a neural network on masses, because you could skip the physics. For example, if you fit on the neural networks will never tell you about shell numbers, magic numbers, right? Yes. If people speculate about the existence of new magic numbers, but this can be done only within a model, right? You have a quantum mechanical models and you can rely on that. But neural networks would be blind. So if there is new physics, you will not see. Neural network fits only the data that you use, that you feed, right, to the neural network. So all the physics that it's outside this bunch of data is not seen, right? It cannot do magic. So the idea is, let's train the neural network on the residue, and let's use it to make a prediction, to improve the predictions of few units out. So this is what we have done. The results are still preliminary because there are some mistakes, but here we have the black is the Duflo-Zucker mass model as it is. And then we use the residue of this model to train a neural network, and we obtain this green line. So you see that the neural network is not doing much, or there is a little bit of improving, right, in the region of the fit. So it looks like the residuals are more looking like white noise. Okay, take this statement with a grain of salt, because we didn't make all the statistical tests, so this is still work in progress. But we can use them to make the extrapolation. So we can use the knowledge, the Duflo-Zucker plus the trained neural network to extrapolate, and these green are now the extrapolated masses. And now you see that somehow these extrapolated masses seems to get closer, or at least they seems to be compatible with the predicted experimental values. And for copper, it's even better. And let's say these error bars seems to be a little bit more realistic. Of course, this is not the end of the story, because the last points of these neural networks are not well trained. It will be actually they are probably wrong. We are still working on that. But the idea is, since in the outer crust I need to make relatively small extrapolation, maybe I can improve the predictions of my model by combining the model plus the neural network. So I'm not the first one who did that, actually. I have to give credit to Professor Piezarevich and his student Utama, who published a paper since 2017, and they showed that the previous inconsistency that I showed before, yes, here, this paper here, if you take the residue of different mass models and you run for each of them a neural network, of course you will get different neural networks. Yeah. But once you use the model plus the neural network, the predictions seems to be compatible. They are not exactly the same, of course, but they seems to solve at least some of the problems of very scattered data. And the results are compatible, of course, within the error bars. So there is a possible line of research in this direction. And, there is also the work, the group in MSU, Professor Nazarevich is doing the same. So he published a recent paper on 2 neutron separation energy and the position of the drip line in calcium isotopes. And again, this is based on neural networks and other machine learning techniques. But the idea is, okay, we know that our models contain errors. We know they are not perfect. So either, of course, a strategy is we improve the model, or if we need to make some extrapolation that are not too extreme, at least for the outer crust, it could be the case, we could simply close our eyes and use statistical methods to at least get an improvement of the prediction. Of course, this is a first step, right? It's not the end of the story. So here I just show you the value of the chemical composition of the crust. In one case done with the Duflo-Zucker plus the neural network, and in one case done with extrapolated masses. So where is it? Yes. So this was Duflo-Zucker, and this is Duflo-Zucker plus the extrapolated masses. So the extrapolated masses are the values that tabulated in the paper of Wang 2016. So the mass table, right? And you see that if you look at the extrapolated masses and Duflo-Zucker, just beyond the last known value, we have something different, right? We have that Duflo-Zucker predicts copper, while the other not. And if I run now the Duflo-Zucker plus neural network, I get now the same sequence, apart, of course, from the very end, where the very end is a big extrapolation. But at least in terms of the first nuclei beyond the experimentally known region, it seems that the results are encouraging. So we are somehow solving this discrepancy of the models. Again, neural networks should not be used as a black box, because of course they don't know anything about the physics, and we have no idea what they learn. So this is a new line of research. So the paper started coming out since 2017. So I hope that more people will work on that, and we will learn more on how to use these tools that are very powerful, but also very dangerous. Now, as you see, I'm very ambitious. I put 44 slides, but I probably will not have time to speak about all of them. And I want now to move quickly to the other region of the crust of the star and speak about the inner crust. And again, I wanted to speak about this region because even here we found a very interesting machine learning algorithm that may help us improving the knowledge of the star. So quickly, this region of the star, as I said, is formed by nuclei surrounded by a gas of neutrons. So it's very important to take into account all the aspects of the interaction. So you have to take into account, you cannot consider just a nucleus plus a gas, but the fact that you put a nucleus into a gas of neutrons, you change the surface properties of the nucleus itself. So the nuclei here are bigger than that you can find on Earth. You see, I have 1,800. Of course, they are bound not by the strong force, but they are bound by the pressure. So, but to give you an idea of how exotic we are. And moreover, all these nuclei are superfluid, and superfluidity here plays a crucial role. You should also take into account that these nuclei form a lattice, so there could be vibrational modes in this lattice. There are vortices. I mean, there are plenty of fascinating phenomena, and to treat them all within a model, it's very hard. So at present, DFT, so density functional theory, is the only one that is really able to solve, to treat this system. But we will see there are problems in using the models. So quickly, what we want is to use a standard Wigner-sized cell approximation, and we want to calculate the energy of a Wigner-sized cell and determine the chemical composition of a Wigner-sized cell by minimizing the total energy of the system, which is the nuclear part plus the electron, right? And the nuclear, I mean the nucleus plus the gas. So people try to not to do this job correctly, and they tend to use semi-classical methods instead. Why? Because if you have to run a DFT calculation for a neutron star, it takes hours for a single calculation, several hours. And I don't even discuss the issues of convergency and the numerical issues that maybe some of you are aware of. So people prefer to use fast methods like Thomas Fermi. The point is that you pay a price. Is that, for example, when people do Thomas Fermi calculation, they ignore superfluidity, which is one of the major components of the crust. So this is a mistake, and one has to deal with this mistake. As I said, the best would be, of course, to treat everything with HFB, and this is what we have done. But there is a price to pay. Maybe I skip this part on terms of the accuracy. Here I wanted just to highlight when I speak about mistakes. So something that should be common in our domain, and I'm pushing in this direction, is that when people say I use a model instead of another because it's more precise, people should quantify. Okay, so it's always good to quantify the mistake we do or the approximation we use. Otherwise, it's nonsense, right? Because I cannot say HFB has problems of finite size that are related to the way HFB equations are solved in the Wigner-sized cell, and then I prefer to use Thomas Fermi, but without judging how good or how bad is the approximation. So what I try to do, and still work in progress, is I try to run all the models in under same condition and compare the result and estimate an error. And for example, what I estimated here is that the biggest error that we do is when we neglect superfluidity. Okay, so although people think that discretization of continuum states, this is what I call finite size effects, are important and are a source of error, and this has been a long discussion that started by Baldo paper in 10 years ago, something like that. But in reality, the bigger error is neglecting superfluidity. So if you want to discuss this region of the star, you should at least take into account the fact that neutrons are superfluid. So I skip this part, this is not relevant. So what we have done is that, okay, we want to take into account superfluidity, but if I want to do that and using a proper density functional theory model, this is very time consuming, right? Because I need to minimize the total energy of the system, where is it? That is this one, as a function of z, so for different values of z, and for different values of the Wigner size cell, because the size of the Wigner size depends on depends on the condition on the beta equilibrium. So all these parts change. So it means that effectively you have to calculate a grid, right, in terms of z and in terms of the density or the baryonic density of the system. And for each point you have to calculate this equation. And these are several hours of work. So here maybe I have the slide. Yeah, this is how it looks like, right? This is the density of the system, so that represent the different layers of the star, and these are the values of Z, so the number of protons. And for each value of the density, I should cut horizontally and find the minimal point. So these are the figures. Where are they? This one, for example, right? So for each value of Z, you calculate the energy per particle, the total energy per particle within the Wigner-sized cell, and then you look for the minimum. And you see that these curves are not smooth. There are a lot of zigzags, so it's difficult to predict. So you really have to calculate everything to predict where the minimum is. So with my students, again, we decided to go on the market and see if there was a way to speed up this calculation. And we managed to find this method that is called Gaussian process emulator. And again, it's a machine learning technique that people start to use right now. And this is it's a smart way of fitting, essentially, right? So this is an example. So imagine that you have your true function, right? The exact function is a black curve. No, what I say well, okay, I say the dotted one. Okay, the dotted line is the true curve. Okay, doesn't matter. And here I assume that this is not a computer simulation. Let's say that this is an experiment. So I make an experiment. So I probe this real model, and these are the red dots with error bars. Of course, if it was a computer simulation, these red dots would stay on top of the blue dotted line. And then, okay, what I do is to fit, and I fit without making any assumption. So I make an assumption on this GPE. So there are underlying assumptions, but let's suppose that I'm not saying, okay, I fit with a straight line, or I fit with a polynomial, or I fit with any other type of function. And this object, this GPE, is able to find the best fit, and this is the black line, with error bars. And you see that this is with 10 points. In the other panel, when I increase the number of points, so increase the number of information, you see that the black line gets closer to true value. So our idea is, I have this surface that is very complex. Maybe I can try to use less points to fit this surface, and then on the emulated surface, so the fitted one, find the minima. So this is what we try to do with my student. So we run this GPE simulator emulation over this grid of points. Of course, this is a test case, so I calculated the entire surface on a grid with a lot of calculation, and with only 1/10 of the points, we were able to fit the surface quite well. So this is actually the difference, right, between the original and the emulated surface. And these are units of mega electron volt. So it's still not perfect because the differences are still quite large, but it's an improvement, right? So we were able to grasp the main structure, apart from maybe from a couple of regions where the emulator didn't do well. But I have to say that there are plenty of options with the emulators in terms of kernels that you can choose, and we just went for the simplest solution. So also this can be improved and so on. So here this is the final result. Let's say I compared to since I have the entire grid of points, I try to compare the let's say true values that are these red ones that are obtained with a spline interpolation of my points, so very high precision, with the prediction made with the Gaussian process emulator and using only 10% of the points. And you see that the results are reasonably well in agreement given the error bars. So the shaded area is the error bars. Maybe for the expert in the field, you will notice that the baryonic density that I wrote here is not very high. I wrote only 1/4 of the actual core crust transition. So I didn't go to very high density because my model was failing, right? You see that the difference between the emulator and the original was of order of 100 kV, and here you see that the differences are becoming of that order of magnitude. So there is no point in going higher in density. The energy difference between the minima are so small that my errors at the moment are too large that it makes no sense, right, to continue. But the idea was, okay, at least I'm working on these tools to speed up the calculation. And again, if I have a better model in the future, maybe an HFB model with a better treatment of continuum states, that is something that is possible, I will be able to run the calculation because I will have also at end these useful statistical tools. So I think that my time is running out. So I want to shorten a little bit the presentation. So maybe if you have questions, we can discuss later. So here is the result. So again, we produced the chemical composition of the star, or at least for part of the crust, and the solid line is the prediction, and I added with dots the error. So you see that the error that comes from estimated numerical error in this case, and you see that in the very low dense region we still have some good accuracy, so there is uncertainties of a couple of units in terms of Z, but when we move to high region, the model is not good enough because the error bars are so large that it makes no sense to discuss anything in this region. Of course, this, if we want to improve two things, one thing is we need better model, because here I just took something that exists on the market, but we need also better solver, because this is a major challenge. Again, maybe some of you know about this. It's a major challenge to describe fully quantum mechanically a nucleus in a gas, right? Because there is a problem of treating the continuous states, and really there is plenty of literature on that, plenty of possibilities, but all of them are time consuming. So for me, the bottleneck was the CPU time. So I really worked on that to see if I was able to find method to reduce the CPU time and be competitive with Thomas Fermi. Exactly. So I will skip the part on the core, but I will just let you know that, that we also work on the core of the star. And this was very interesting. This was motivated by recent discoveries of new particles that is called D star, that is a boson. And here in this case, I have to use relativistic mean field because, as you know, Scherm functional, you conserve the mass, so you cannot have new particles. So, so it's interesting. I leave it as a reference if you are interested in this part. So I jump to the conclusion because I think my time is running out. So as you see, I work on the different aspect of nuclear structure. So my main goal is, of course, to improve models, but it's very hard to improve models on their own. So there is an entire line of research on how to build better functionals, maybe different from Scherm, right? You see, if you follow the literature, there are plenty of possibility. Maybe relativistic mean field from the start. I know that one of you is working on that, for example, and this seems to be promising, but this cannot be the only way. We know that all models are wrong because they are all phenomenological, so they are all based on extrapolation. So how to live with extrapolation and have results that are reliable? Well, we need to properly treat statistics and make a statistical analysis, and hopefully on the market there are plenty of tools that could help us. So I think that my take-home message is that I would like to have this unified picture, of course, of treating stars using models that are also created to treat nuclei, but these are models, and as all models, they require a proper statistical treatment. So my goal in the near future is to bring statistics and nuclear physics even closer together to be able to make these extrapolation more reliable, and then use this data for astrophysical calculation, but with error bars. So I stop here. Thanks a lot for listening, and thanks a lot for giving me the opportunity for the webinar.
Thank you. Thank you very much. Any questions?
Boring.
Hello.
Any questions? Yes, any questions?
Yeah, I just want to have one question.
Yes.
Because where the just shows that the mass is, and we're talking about the deuteric nuclei, mostly which are the exotic nuclei. And all those masses are basically derived from experimental masses, are not the mass measured only. They are derived from either by the Q value measurement or these things. So simply because when we are doing the derivations from depending upon some functional form, and that functional form may or may not be exact, because if you be using the most of the nuclei, beta decay nuclei, we use something that the Q values are basically correlated with the half-life also. So when getting the answer that from the Q value we are driving the masses, but we also has to take care of the half-lives or transition probability also.
Mhm. Dan?
Yeah, that's
Yeah, no, you touch a very important point that again, this is something that people start to add in the papers only recently, that are covariance matrices. So we know that there are built-in correlation between observables. In some cases, they look like naturally built-in. Again, I take the example of the neutron skin and slope of symmetry energy, right? In other cases, this correlation may be artificial or created by the model, right? Because you have to, you're constraining a model on some data, and maybe you don't have enough freedom in this model. So these should be taken care, of course. And if your goal is to have a unified description, that the goal of many people working on functional, right? All these points need to be taken into account. That's why, first of all, it's crucial to choose the right pool of observable, right? And it's not just the quantity of observable, but make sure that the observable that you are taking into account, that they are not all correlated among each other. Otherwise, you don't do a good job.
Exactly.
But also
yeah, because
check the statistical, right? When you finish the fit, you should check the covariance matrix and check how the parameters are correlated, because sometimes it's surprising how the parameters are correlated. So when you fit one, all the others are fitted, are constrained. So when you say, I have my model have 5 parameters, in reality, maybe you have only 2 that are free. So these are important aspects that the one should take care of, but this was not done before. Somehow was done, let's say, under in the corridors. So people that do fit know about this. People that do not fit have no clue. But now finally, this is appearing also in the paper. So at least, I mean, there is no point in adding observable for observable. You have really to pay attention on what to fit and how, and the correlation, and all these things are really crucial points.
okay. Second, I did not understand that why we have only the Gaussian illuminators, why not others?
Yes.
So why we only have Gaussian illuminators?
No, it's one choice. It's Gaussian, but it's a choice of the kernel. But you can have different kernels.
Okay, thank you.
There are. I mean, again, I'm not the expert on this. Gaussian is the simplest things because you can make infinite times the derivative and so on. I mean, but there are different kernels. So there is all. You can have a look at the literature, and this was started by O'Higgins. So the entire literature now on that, statisticians are working on that. Is really a lot of work to enter in that, but I think it could be promising, because we often do extrapolation, and this could be, I mean, the results that were presented by Utama and Nazarevich on 2 neutron separation energies were very, very encouraging. Of course, these are the only 2. I don't know if this is.
Yeah, thank you very much for good. It's a very, very light minute talk. Thank you.
Thank to you.
Alexandro,
Yes.
can you tell us what kind of tools you are using for this neural network?
Okay, so these neural network are now standard packages in Python. So what I've done with the student is that I'm not good in building a neural network. So that was, we took a package that is called Waka from Python.
How do you spell?
W-A-K-A, Waka. It's the name of a New Zealand bird.
Okay,
So
okay.
it's Waka with a K or with a C. I have to check. But if you look, these are packages that are in Python. So it's we didn't invent anything, and it's the same. If you can find all the references, that this is a good thing on the PhD thesis of Utama that is published. So you can find the PhD.
Yes.
Utama
Who is
PhD.
the co-author of Pikarevich?
Say it again.
He is the co-author of Pikarevich. He has wrote the paper with Pikarevich. You're talking about that person?
Yes.
Okay, okay,
Yeah.
okay.
There is a thesis. I found it on Google, so you should be able to find it. If you don't find it, send me an email. I can send it to you. And
Sure.
there all detailed what he did in terms of neural network. But I have the impression that I don't know if he's a man or a lady. I have no idea. So let's assume a man because it's a standard. But if he, I have the impression that he didn't write his own package, but he took this package, because building a neural network from scratch, it can be complicated. But
Exactly.
But
Yeah, they
all
are
these
very,
things exist.
yeah.
Really,
Yes.
they are big libraries in Python. So
Okay. So these are similar to like what we call TensorFlow or Keras or something like that. Is Waka is something of that kind?
now I don't know this what this TensorFlow, let's say.
TensorFlow or Keras.
I never heard about that. Honestly,
Okay.
I've done a school on Bayesian neural network.
I know. Yes, my student Tuhir Malik was there with you in
okay,
last
so
school. Yeah,
you see the lecture. You can ask him because the lecturer made something on that. But again, they use already written Python packages. So nobody builds from scratch a neural network. What you do is that you play with the nodes, you play with the layers. You don't build it from scratch.
Exactly.
So then we use Python because apparently Python now is becoming the tool of choice, right? Because everyone codes Python.
Yes.
And otherwise, you can also look for the tutorials of the Sheffield group here in the UK. There is a group in statistics that is very famous for these machine learning methods. So really, you have to look at the statistician because they do this for a living. There are plenty of tools available.
Yes.
And the best is that if you find someone that knows about them, because otherwise, as I said, there are black boxes that are very dangerous. I mean, with the student, it took us a lot to understand what we were actually doing.
Okay.
Because the danger of these things is the overfitting. Huh?
Yes, that is very true. Very true.
Actually, when I look at the criteria to avoid overfitting, is that you fit until you overfit. When you start overfitting, you stop. Okay, well, cool.
Yes.
So that's why also my results still working on them, because there are good things. So there are things that are under control, but not 100%. So I'm still working. So the is not final.
Okay. Actually, we are trying to develop some sort of this network for one of my calculations.
I don't hear you.
We are trying to build up some network for some of the calculation. So maybe I will send you those results and I will ask you for your feedback, because I know this overfitting and all, these are very serious problem in this kind of calculation. So I will.
I mean, I'm not the expert on the domain, right? I didn't write anything, but I'm very happy to be involved in these things, because I'm trying with my colleague. He's an experimentalist. He's trying to apply the same methods in experimental physics. So we will have again another student this year working on this. and it's a more try and fail procedure, right? Because we take these packages, we learn how they work, we see how we get the results, and then I would like to do more, but unfortunately is that when you have to read this paper in statistics, they are completely different languages, it's complicated. It would be much easier for someone that tells you how to do it.
Exactly. No, because I find it fascinating because you see, until 2 3 years back, we did not know how to deal with systematic error. Now, with the help of this neural network, it looks like that we can improve on systematic error also because I mean that is a regime where we don't have any model. So their neural network is a big help actually.
Yes.
Okay, any more question?
Sure, yeah.
I have one question. Hello, I'm Chiranjeev. The question I have is that when you are working on the outer crust, you have this plethora of binding energy known to us from our experiments done in the terrestrial condition, and we use all these sophisticated statistical tools to extend the theory to know the constituent of the crust, the outer crust. But now when we reach the domain of the inner crust, for example, I'm not even going into the core. I mean, when we are going into the inner crust, I mean, where should be the limit of the statistical tools to convince yourself that okay, let's draw the line here? Because for statistical tools to work, you have to have some experimental quantities to feed the theory to improve the statistics. But if you don't have any idea how to achieve them, where do you draw the line? I mean, I am always puzzled with this.
You're absolutely correct. And for the moment, I had ideas on how to propagate the error only on outer crust, right? Because that's the standard condition. In principle, one could propagate statistical errors also in the inner crust, because it's just the error of the coupling constant. There are ways to do it, right? It's just with the derivative of the observable respect to parameters times the covariance. This is possible. To me, makes little sense because while the outer crust somehow the model is clear, you could believe easily. Well, believe you could say that okay, the BCC configuration is okay, that a single nucleus configuration for Wigner size is okay, right? You are assuming that there are no molecules, that there are no other lattice configuration. Okay, let's leave this aside. Well, when you move to the inner crust, then you have other uncertainties that are, in that case, probably the single nucleus approximation is a very poor one, because when you look at the energy curves, you see that the different minima are they are what 10 kV apart from each other.
Yes,
It's nothing,
yes.
right? So you could have other, you could have phonons, right? It's a lattice, so there could be a lattice vibration. So a phonon could come and change the composition. I mean, it could be more mixed than what we expect. So before working on the functional, I would also work on the model itself of the crust, because I'm not sure that the model is correct. And moreover, what we use in terms of a solver, you see, most of the people use Thomas Fermi. Well, Thomas Fermi, you neglect completely superfluidity. Other people use compressible liquid drop model. So you do completely forget shell effects. I use HFB, and I know that the way I use HFB, I do a poor job with continuum state. So before even touching the functional, still I should probably improve with the solver and maybe have a better description of the inner crust. So here in this case, probably you're right, making an error propagation of the makes a little sense. Here, what I call error were more, let's say, numerical errors related to my solver.
Yes,
And not,
yes.
you're absolutely right. I would not push more than the outer crust, because there really it's pure extrapolation, and the error bars would be simply huge, and you would understand that.
Okay. Thank you very much for the answer. And I have just very similar question. I mean, in this regard, that now that we have these neutron star merging events coming up almost every other month from these LIGO and Virgo experiments, I mean observations. I mean, is there any kind of crude observable which can be directly related to the structure of the inner crust or even beyond? I mean, when they merge, mostly you get the information on the outer crust because they are the ones which are more viable to give you something from the merging. What are the prospects of finding something about beyond the outer crust?
That's an excellent question, and but to answer this question, first of all, one should be able to run a calculation from the beginning to the end, right? So one should be able to inject a functional, calculate an equation of state out of bit equilibrium at finite temperature, inject it into a hydrodynamic code, make a merging simulation, and see what it comes out.
Okay.
Well, right? Because we have
yeah.
right. And then I don't know if you want to look at electromagnetic observables, then you have to put this into a code that does this calculation, and so the point, the problem here is that we as nuclear physicists, we are at the beginning of the process, but our model is then used at least in other 2 models, or more. So each time you use a model into another model, then you add uncertainty, you add errors, and usually these calculations are done in a patchy way. I see that there is really a lack of communication, in my impression, between astro and nuclear. So people just take what's on the market, they don't care. So historically, people use the equation of state with a compressibility of 400 stuff.
Yes.
So there is no point in doing calculation like that. So if we are able to improve, maybe with the new generation, to improve the flow of communication, and then you could propagate and say, look, I use this equation of state that has this approximation or this other, and I see a different effect on the gravitational wave. Maybe, but you have to do the calculation in a consistent way, and at the moment I don't see it. But why not? I mean, till a few years ago, people didn't even think about gravitational waves. Now we have this new signal. Now, how to model it? Maybe in 10 years' time, this will be kind of routine observable that we will put in our feed. I don't know.
Thank you.
I think time is 1.5 hours, so okay, thank you. That's it. Thank you very much.
Thank you.
Okay, thank you very much, Alessandro.
Thank you.
Thank you very much. It was really exploring talk. I mean, I really enjoyed it.
Thank you so much. Okay.
Okay.
Okay, thank you very much.
Bye.
Bye.
Bye.